Okay, you can see my screen, right?
Yes, sir.
Okay. Yeah, so we were discussing just some syntax, the free and bound variables inside quantified formulas. Okay, so we had some examples there. Hi, Diganta. Hello?
Hello. Yeah. Hello.
Yeah, okay, good. So any questions here? This is a purely a syntactic concept, and I've shown you some example from this quantified Boolean formula. See, the concept of bound and free variables is much like scoping in programming languages. Okay, so when inside in this formula, in this sub formula here, informally, I mean, I haven't defined the semantics, formal semantics yet, but informally, what does this highlighted sub-formula of psi1, which reads, there exists a y such that w. So here we are assuming that these variables are ranging over a Boolean domain, okay? And they take 0 or 1 values. That's why this is called quantified Boolean formula, although first order predicate in first order predicate logic, these variables can range over any domains. So for the moment, let's assume. So here, both in this formula, W and Z are free. So only Y is bound. Because specifically for this Y, so this is asking, does there exist a Y such that W or Y and Z is true? Yeah, I haven't introduced the formal semantic, which I will introduce a little bit starting with the next slide. For one of you, can you tell me what this, if this is true, if there is, I mean, the bound means there is a specific wise, because I'm referring to this existential, making this existential assertions with respect to y, and therefore y is bound, whereas w and z in this formula are free in the sense that they can take any value, okay? Whereas y I'm making a specific reference to in the existential. Okay?
Sir, if Z and W are 0, then like there won't exist any Y.
Correct. So for example, you're exactly right. So then this formula is not, does not hold. It is unsatisfiable, right? Because no matter what you, oh no, I'm sorry. Yeah, if you make W and Z to be 0, then this is false because there does not exist a Y. Now the concept of freeness means that you're allowed to instantiate it in whatever way you want. Okay, so that's what this thing means. Okay, so similarly, when you have here in this whole thing, yeah, Z is bound by this, the outer this thing, but W is still left free. So, and that's right. So the idea of when it's free, it is like, when you give meaning to it, you can instantiate that by anything. Whereas when you have a bound variable, they take on specific meanings, and that's what this thing is. That's all. Yeah. Now, so here is the thing: if no variables occur free in a formula, that is, if every variable is bound by one of the quantifiers, then it is said to be a sentence. Otherwise, it's just a formula which has some free variables. So there are some variables which are not bound. Like I said, they can take in the interpretation. You can make sense out of formulas that are not sentences only by giving some specific interpretation or assignments to those variables. Otherwise, you won't be able to assign a specific meaning to that. And that's why this notion, the syntactic notion of which is bound and which is free, is important. Okay. So now, starting with this line, I define the rules that give meaning to formulas. That is truth assignment to formulas in first order logic. But also, in any logic, we use the thing model or interpretation. These are interchangeable use also for the structure to determine the truth of a formula. For propositional logic, since they were only, there were only propositional variables there, the model was just a truth assignment, simple truth assignment to the propositional variables in the thing. Whereas here, there are several other syntactic, symbols that need to be given meaning or interpretation to in order to, before you could assign a truth value to a formula. So for example, here we talk about domains, okay? These domains can be some specific domains, some discrete domains, and interpreted domains like natural numbers and so on. So you need to assign a domain, okay? For the time being, we will assume that we will have a single domain, okay? And you will see all these notions that I introduced can then be naturally extended to logics that have multiple sorts or multiple domains. But for the moment, let's assume that we have a single domain. So we need to give meaning to what the elements, what this domain is, what kind of members this domain contains. Okay, so so for example, the two things. Logic that I introduced before. This is what I call the set theory and elementary set. Elementary set theory. They had a domain over which we were defining functions, predicates, and so on. So we never, you could instantiate those domain to anything you want. Okay, so for any specific domain. So that is part of giving semantics. You have to first specify what the domain, the set of elements, okay, are that the variables can be made to denote, and the functions and predicates are defined over. And for every constant, okay, before that, all these, there's something called a signature. A signature it consists all the non-logical entities, okay, like functions, constant symbols, domain, starting with a domain that for which you need to give a meaning for before you can attach. So that is the collection of all non-logical entities are what is called the signature. Okay? Specifically, they include the domain, the function symbols, the constant symbols, and predicate symbols. So given, we need to give first, so the collection is what's called signature. So a mapping then, for each constant that is included in the signature of the language, you need to associate a constant, an element, some specific element from the domain. For each function symbol, an NRE function symbol that is in the signature, you need to associate an actual function, NRE function that maps an n tuple of elements drawn from the domain to another element from the same domain. A predicate is like a relation. Okay, a relation is, as you know, is a subset. Okay, any subset of the domain. So if it's an NRE predicate, then you will have for each predicate symbol, you have a subset of the thing. So the convention is that anything that belongs to this subset, the predicate is said to be true. Okay. Or in formal terms, the predicate, this relation characterizes those elements of that for which that predicate is true. If it's an NRE predicate, then it will be a relation, which means a subset of n tuples. For example, so here, you remember that we had this less than in the in this language that we had some examples of language in this elementary thing. If we assume that the domain, we use the standard natural number as the domain for this, then the members of the domain will be 0, 1, 2, 3, etc. And this predicate symbol less than, if you assume we want to give it the standard less than meaning, when viewed as a relation over, so that predicate is a binary predicate, therefore it the meaning you associate with that is a binary relation, which means that it is just a subset of pairs of set of all pairs of elements. So if you assume that we want to assuming that we want to give the standard less than interpretation for it, then that contains the less than will the predicate less than the interpretation of the predicate less than will is a relation that contains these tuples. Since 0 is less than 1, therefore 0, 1 belongs to that. Then 0, 1, 1, 2, 1, 3, all of them belong to that. Okay, there is an extra thing in here. Yeah. So then 2, 3, 2, 4, 2, 5, 2, 6, etc., etc., etc. Okay. So that's what this thing is. Is that so? This is so less than pretty much it is defined as a binary relation, which really in mathematics, in discrete math, that actually denotes a subset of the set of all pairs of numbers. And the assumption is that for each of these elements that are in the set, the predicate is true. For everything else that is not in the set, the predicate is assumed to be false. Okay? Yeah, and for functions, for example, in that examples, if you had plus, you had successor, then you would naturally associate appropriate function of appropriate arity to that. So so that's that is the first part. Okay, before you can give truth values for the thing. So once you have the interpretation given to each of the syntactic symbols, non-logical symbols in the signature. Now you're ready to give meaning to the terms in the language. Okay. I mean, I already have an example. Consider the signature corresponding to the language of set theory. Okay. The set theory had a single predicate symbol, epsilon. Okay. I mean, and it had a constant symbol, 0. So if we give the interpretation, the domain, if you want to say, we want to define that over the set of natural numbers, then the constant 0 in that, okay, so then one way of a possible model for that thing is 0 is mapped to the 0, the element 0 in the set of natural numbers, and epsilon, which was a syntax, which is part of the signature. We can choose to associate that with the less than predicate that is defined on natural numbers. Okay. And then this becomes, this is a legal formula. So given that interpretation to the symbols in the signature, now, we can then now say, ready to attach meaning to a formula. Okay. So this is a well-formed formula in that, in the language. So given this interpretation, what is the truth value of this formula? Is it true or false? Well, what is it saying is there exists an x such that for all y, it is not the case. There exists some x, okay, that is such that every y is not less than, that is greater than or equal to 0. Yes?
Sir, I had a question. Like, I actually thought this was like not y. What would that mean?
What would that mean?
Yes.
That means that y should not be less than x.
Okay. But like, if someone were to like just single for all y, not y, something like that, would that make any sense?
Say that again. For all y? Not y.
Yes, not y.
Just think about it. Well,
Okay.
for all y, not y. First of all, that's not a not is applicable. It's a logical connector. So it is an operation meant to be used only for on
Like truth, Boolean.
formulas, right? Formulas. So logical connectives can be applied only to formulas. So y here is a variable that is ranging over the domain. Okay, so it's not a formula. Therefore, not y. For all y, not y is not a well-formed formula. Okay, so you remember that the way we constructed our the atomic, our formulas were from atomic formulas. And what was an atomic formula? It was, I mean, if you had allowed propositional variables also, then it is one thing. Here I'm assuming that we have a single domain, okay, which is not, okay, the variables are ranging over that particular domain. Okay, so if you don't have any non-logical things, and if you're then if you only allow propositional variables, then y would be a proposition variable. That's what happened in propositional logic. Okay. So of course you could have propositional variables also, but here, since I'm limiting myself for the purpose of this lecture, only a single sort. Okay. So and then we assume that particular. So the variables are only ranging over that domain, which is assigned as natural number. For that, it doesn't make. So we are not allowing propositional variables here. So the variables here are all ranging over natural numbers. Therefore, not is only defined for formula. That is the specific reason. Yeah.
Yep.
Okay. So, but yeah, so that's why the only way you can get formulas here is by starting with the predicate symbol epsilon. Okay.
Okay.
So who's this? Who's asking this question?
This is Harsh.
Harsh. Okay. So by the way, Amaya, how do you pronounce your name? Amaya? Amaya?
Ameya.
Amaya.
Ameya. It's Ameya.
Yeah,
Yeah.
Amaya. So that is clear to you, no?
Yes, yes, sir.
Yeah. Okay. So why this things, and here you can have, you know, all formulas here are constructed from the unique predicate symbol that you have. I mean epsilon. Yeah. Okay. So given
Yeah.
that, is this true here?
Yes, sir, it's true. You can put x is 0, then you'll get.
Exactly. Yeah. Yeah. So x is 0. So 0 is something. Is something, you know, for which this is true, because for all y it is not the case. For all y, including 0, it is not the case that y is less than x. Okay, if you so by making x to be 0, you can make this to be true, because 0 is also not less than 0. Okay, because 0 is actually equal. Huh? That's one. Yeah, so this is kind of you can say that this is not standard set theory or anything. This is not the way you would provide interpretation. I'm here giving this interpretation, which may not be a very standard interpretation, just to say that, okay, look, you have these language which have function symbols which don't have any meaning. Sometimes, you know, without any meaning, those function symbols are called uninterpreted. Okay, so but you could give any meaning you want. Okay, you can choose any domain you want. Okay, as a matter of fact, you can choose even an empty domain for that matter. Okay, and in which case all functions will be empty, all predicates will be empty. So it may not be very interesting, but that can also be a model. Okay, a possible model for those things. If you choose your domain to be empty, then all your there can't be any constant symbols in such a language, because there's no meaning for the constant symbols to assign to, and you know, there won't be, the variables will be a thing. So we will see. So then that won't be very interesting, but you can choose empty domain, a domain which only has one element, whatever that you want. Okay, and once you choose that, then all your the truth value assignments to formulas as well as terms, etc., will be relative to the interpretation that you give for the syntactic elements, okay, in your signature. Yeah, so like it was pointed out. So I'm going slow, okay? So if you think that I'm too slow, you can think. And I think all the rest of the people who have expressed interest in taking it, maybe you know, they didn't show up today because they have gone through these things, and I'm going, you know, quite slow. Yeah, so this slide is not needed. So now, before you start giving meaning to formulas, you first have to start by giving meaning, interpretation to terms, okay, and predicate symbols in your signature. Okay, and this is done. And since terms are built from other variables, so you can only assign a meaning to a term given some variable assignment to the variables in the term, unless the term is built only out of constants and function symbols. Then of course you can define, but in general they are allowed to contain variables, and therefore you will have to give the meaning for a term Yeah. So in general, like in propositional logic, that giving what you're defining is this double turn style, and then given a model and given a assignment to the variables inside a formula, get assignment for each of the variables assignment to each of the variables an element, okay, mapping for each of the variables an element in the domain. You have to define what phi s, okay, means. That's how you read this. This in the model and the structure that is given, then phi for a variable assignment is true. Okay, that's how you define. So whereas there you did not, for proposition logic, M was not necessary. Okay, because you only had logical connectives and your propositional variables took just true or false, and M was not needed. So to define this formula, first you have to give interpretation for the terms, and that's what this S bar gives you. S bar is pretty much like an evaluation function. So given values to the variables in the term, it kind of recursively evaluates these functions by applying the actual function that is that particular function symbol is mapped to. Okay, and we define this recursively. So for variables, S for any variable, what S bar gives you is just whatever the value that X is mapped to by the variable assignment S. And for each constant symbol, S bar of C will give you whatever interpretation that you assign to the constant symbol. And given already some interpretation for T1, Tn as per S bar, so the meaning that S bar interpretation associates with the term of which denotes the application of F to these n terms is just applying the interpretation that is given by the model F to this function symbol Fn to the interpretation that you get for each of these terms. Okay, so this is how you kind of do. So if you were to be evaluating an expression or a term, so a term denotes an expression. So that's what this thing is defined. Yeah. Yeah. So is that clear? So for example, that's what I had in here. So instead of S bar, I'm using SS. So now you can, given this, you can now assign a meaning to this thing. Okay. So given the model, if I'm assuming that the model for this elementary number theory language that I had introduced earlier, so this has to suppose that I'm using the standard natural number. For successor, I'm using increment by 1. For plus, star, and exponentiation, the standard functions defined over the natural numbers. Then specifically what this interpretation for this term, syntactic term, will be this one. Okay, by you just recursively evaluate them. Starting from 0, successor of 0 gives you 0 plus 1, and applying another successor will add another plus 1, and then the plus will add, and similarly for successor of 0, and then you could 0 plus 1 is actually 1, 1 plus 1 is 2, 2 plus 1, and then it will be 3. Okay. Similarly, now you can give for the same for predicates, and that's what this thing is doing here. Okay. So here we start assigning truth values for formulas. Now starting with atomic formulas. So what are the atomic formulas? We assume that we have equality. Okay. So equality can be applied to any two terms. That's how it's done. So you get the interpretation. If the interpretation that you S bar assigns for T1 and T2 are actually equal as per the equality, okay? So they're identical, then it is true, otherwise it is false. For an arbitrary predicate, you just have to check if it is, if the that tuple that you get, giving, by evaluating or giving, I mean, I use informally the term evaluating. The terms T1 through Tn belongs to that relation. And that's how I'm giving, the semantics for less than, okay? Because this is true, okay? Why? Because when you evaluate this term using SS, that gives you 1, right? No, 1 plus 2, 3, okay? And 3 is indeed less than 0, because 3 is 0. 0, comma 3 belongs to that thing. So that's all. So it's basically evaluating those things as per. Now, all the meaning for all the rest of the formulas are given as follows. So if you already know what the truth assignment for phi is, not of phi, given a model and variable assignment, it is, it holds if and only if phi for the same variable assignment does not hold, okay? Which is exactly how we define, because that's a logical connective, and that's how you define it in propositional. But here you will be evaluating the truth assignment as per the, given the model as well. We need the model as well. So this is saying for implication, either phi is false, does not hold in the model for the variable assignment, or if psi should hold. So that's all standard, as in propositional logic. The only new thing here is for all the quantifiers. I mean, there are actually two new things in the way that we assign meaning to predicate and functional terms, given the model and variable assignment. And after that, here is, so for all x, phi of s is true if, when you replace every variable in the formula by the corresponding value assigned by the variable assignment to that variable, then you use the, then you interpret that formula, which now does not have any variables, only, so does not have any variables, as per, the rules. If that holds, then that should hold for every element in the domain, okay? So here, x vertical bar d means you, the function is, so here you see you're replacing only the bound variables, okay? It's the bound, okay, what you're doing is, basically what you're doing is, you're modifying, this is a modification operation to the variable assignment, okay? So the variable assignment assigns values to all the variables, including x, okay? It's only for the bound variable that you change the variable assignment. I mean, here you're saying, okay, you will have to check, okay, for every assignment in which you assign, for every element in the domain M, if you change S in only one variable, in the bound variable, for all the rest, okay, which are not bound by this, which means which are free, okay, then it should, that is the operation that S of X of D is doing, okay? It's just changing S, the value assignment, in one place, okay, specifically for this variable to D. That's what it means. Now, but then you have to check this for it to be true for every element. Okay. Now, existential quantification can then be derived by assuming it exists V alpha for some alpha, is defined as not of for all v, not of alpha. Okay, so that I don't have to. Now you can give a meaning directly also by saying, okay, now this is true if alpha of as there exists a member of this domain. Okay. Any questions here? This is just a kind of an elaborate, a very verbose way of saying, okay, you replace, check if this is for all x is true. If you replace that particular bound variable by d for every element in the d, it should be true. Okay, that's what that is. Okay, so I will go through some. Maybe there is example here. No, there'll be some examples later on. And that's how that you interpret it. You remember that this particular thing that you had. So now, okay, yeah. So that's how that you interpret here. So let's suppose my domain is just which has two elements, ones and zero, and the truth value, and that's how that you are able to get the meaning for these for these things. Okay. By the way, there is one convention which is kind of a corner case for which you will have to know. So what happens if you had an empty domain? If your domain were empty, what is the meaning of for all? There's no value in the domain to replace your variables with. Okay, so yeah,
maybe that would be like vacuously true.
Yeah,
that would be vacuously true.
vacuously true. That's yes. You could say why, but that's yes, because there's no. I mean, it is in some sense for all elements. Okay, there's no element, and therefore for all x for an empty domain is vacuously true, and therefore for the same reason there exists an x will be vacuously false. Okay, so that is something that's a corner case that you will have to bear in mind. Okay. Yeah. So these are some definitions that you will see that are used in logic standards. So given a set of so a sigma formula, just a fancy way of saying a formula that is well formed using the symbols in the signature sigma. That's all. Okay. So if tau is a set of sigma formulas, we write it this way, okay? I mean, yeah, to say that every formula in that set is true. So for given a variable assignment S and M, for every formula, yeah, that is true. So this is used to define this thing. So that some formula semantically holds as a consequence given a set of assumptions. Okay, so we are trying to define this one. So given a set of assumptions, which are premises, which are some, if you assume a set of formulas here in tau, then phi is true. Okay, what does that mean logically? Okay, semantically, what it means is for every model M and for every variable assignment S, such that for which every formula in tau holds good, if then so should then if it's the case that phi will hold for that model for the same, for that variable assignment as well. Okay? Then you can also write it this way. So given a set of formulas, then we say that as per the rules of assigning the semantics, phi semantically follows as a consequence of the premises sum. Okay. When you say two things are logically equivalent, if and only if that for every model for which every psi holds, and for every variable assignment, phi should hold. Similarly, the reverse. Okay. The only difference is, see, in the case of propositional logic, logical consequence, etc., was validated for all variable assignments, whereas here there is this extra baggage of carrying along the structure, the model, which gives meaning for the interpretations. That's all. Okay. So now, if you're able to show that phi holds for every model for all possible variable assignments for the variable free variables in phi, then without any assumptions, then that's when you write it like this. That's when you say it is valid. Okay. So this denotes validity. So which means that the assumptions is zero. If you're able to show that it holds for every model, that is for every possible interpretation that you can give, and for every possible domains, okay? And this includes empty domain also, okay? For every possible structure that you can construct, okay? And for every possible variable assignments that you can give for the variables. And if phi happens to be true, then it is said to be valid. That's when you say that it is valid. In the case of propositional logic, validity really corresponded to tautology. So the way that you say a formula in propositional logic is a tautology if it is true for every possible truth value assignments to the variables. Okay. And that's what validity was. Here, you extend that with, giving, saying, okay, for every possible structure that you can give. Now, in predicate logic, there are lots of, systems, just like we saw resolution, there are system of inference rules that allow you to deduce validity using the application of set of inference rules, okay? The inference rules for predicate logic is a lot more complex, okay? That's because it has quantifiers and you allow for domains which can be infinite, okay? So it was easy to state it this way semantically by saying, if it is true for every element in the domain, it is true. That's how I say the meaning. So it's another thing to check in a mechanical way that indeed for every element of the domain happens to be infinite. Okay? For propositional logic, because there are only finitely many variables, you could do it even without the inference rules. Whereas here it becomes your inference rules have to be a lot more complex. But anyway, the distinction between assigning this double turnstile and single turnstile still applies to predicate logic as well. Okay. Any questions here before I move to some examples? Okay. So maybe, if anything, I have fluxed you, you have to ask. Okay. I'll take it as a yes. No.
Yes, sir. It's clear for me.
Okay. So here are some examples. So for the moment, you assume we are working, only interpretations with non-empty models. Okay. So now I have a whole bunch of examples. These are all these examples. And later on, I'll show you some kind of, examples that are. So here, a lot of these examples are artificial, and they're also sometimes kind of brain, twisters, okay? But, these examples, for which I give credit to Clark, is made to kind of, check whether you've understood the way that the semantics has been defined. Okay, wrong. So is this true? Does this hold? I mean, this should be interpreted as assuming that this is true for all V1, PV1 is true. Is it the case PV2 is true?
Yes.
Okay. So this was Harsh, is it?
Yes. Like it will be true because it is already true for all V1. So for V2, it should also be true.
Yeah, for P of B2 to be true. So for any model, you see, the reason is, so you have to, okay, so I'm, okay, which you're correct, okay? But I know Ameya was silent. I want to make sure that he understood it.
Yeah, sir, I got it, yes.
Yeah, okay. Now, I think you have to, I'll probe you a little bit more why it is the case, okay? Now, I know that it is intuitively, it is the case, but what was the definition? So when is PV2 is true? So for every model, for every S, okay, is what it says, okay? Is this true even for empty model? See, I mean, this has to be, this is, when we do this, it has to be shown for every possible model, for every possible interpretation for P, okay? Specifically, is it true for empty model?
For empty model, like it should be true, I guess. Like, because vacuously true, right? Like this first statement is already true. Like for empty model, that for all V1, like if the model is empty, there is nothing there.
Yeah, even PV2 should
Yeah.
be true, right?
So
For
V2
empty
will not be
models.
mapped to anything, therefore that's empty. So this is true, including even for empty model. Okay. Yeah, but the way that, yeah, so I made that point only to emphasize that strictly speaking, you have to check this. Okay. This, in order to ensure this, you have to check for all possible models and so on. Yeah.
Yeah.
For all possible value assignments. Okay. Because there's nothing, V2, P is empty. Therefore, there's V2, variable assignment doesn't assign anything to V2. Okay, so that's true. So PV, I'm assuming this only because some of these things you will see that they may not be true. Most of these examples that I give you are true for all, including for empty models, but some are probably not true. That's why I have edited this, okay, to include this. So how about this? Amir?
This is not true, right?
Yeah, why?
Because like if you have a V2, then only V1 is in P.
Yeah.
V2 is not in P.
Although I've tricked you into using the same variable V1, this V1, it's a bound variable. You could have given X, Y, Z, or whatever. Okay. This V1 does not. Okay. So it's because a bound variable. Although here you can make this true for a particular assignment. Yeah.
For empty model, I guess.
Yeah, I mean, in this case, for example, yeah. So no, but for this empty model, even for all V1 will be true. Yeah. So for empty model, specifically for empty model, this kind of holds. Okay. But not for all possible models. Yeah. As soon as a model has at least one, I mean, even for a model for which with a single element. No, even for that, okay, suppose your model had only a single element. But if you give the interpretation for P to be empty, this is no, even for a single element, it is true. So, but starting with models that have two elements, it becomes a problem. Okay, so that's when the thing. So for So then for other interpretations for P, okay, you can see this has to hold good for any interpretation for, for P. You may be able to find specific models with specific interpretation for P where you may make this thing to be true, okay, for it to hold. But the question here I'm raising is that for all models for which this is true, this has to be true. So that's how you have to do it. How about this third?
This is also true, right?
Yeah, this is true.
Yeah. So
Even
from
for
the,
Yeah.
I guess for MT models, this may not be true, okay, because there exists a V2.
Oh,
So
yeah.
I think that's the one for which this was said. So because for MT models, this will be thing. I think for MT models, these corner cases can be a little bit tricky. So for MT models, it's vacuously true, and this one is false, okay. So, but that's where maybe this one is needed, okay. I mean, this is certainly one case for which you need this assumption. The other person, Harsh, you want to take
Uh,
a crack?
I don't think this is true, but let me think for a moment.
So what is it saying? So this is true. There exists an X such that for all Y. Yeah. So this says there exists.
Yeah, there exists.
It's true, right? I think it's true.
Yeah. So this has to be true. There must be an X such that Qx of Y is true for all for all Y. Whereas here, unless so here you are saying.
Okay, yeah, this is just like he just flipped the order. So, in which
No,
it,
they are different, but it is true in this case.
yeah, in this case it works. Uh, maybe. Uh, I mean, you can do this because there is no like y does not is not depending upon x. So I think you can shift it.
Yeah, so this should be for all Y. Yeah, there is the same, there exists an X it's for all QXY, for all, such that for all Y, the same X, correct? Because here, there must be a single. Yes, this is true, but the reverse of that is not true, okay? So here, so because you get this allows different x's. So whereas see when you do this here, this is the strongest statements, okay? Because it's a weaker thing, okay? I mean you're saying that for all y there must be the same x, okay? For all y, for every y you will have to. This is you can pick different things, okay? So that's why, whereas here it requires, actually this one here, this requires the same X, okay? Whereas here, this is kind of weaker. So here, this allows you to pick different X for such that, for different Y. Whereas this one says that you will have to pick the same Y, okay? So that's why this thing is the other one is false. Yeah.
So number 4 will again require not empty models, right?
Yeah, I think whenever you have this exists, you will have you probably require models are empty. Okay, models are non-empty. Okay. Yeah, so I don't know. Yes. Yeah, because see, otherwise what happens is if it's empty, this thing is false. Let's see. For empty, this thing is false. Maybe not in this case. If it's an empty model, this thing is obviously false. No?
I think number 5 is okay, but number 4 will need it, as in the one above, the one you're highlighting.
Yeah. So it's empty. This thing doesn't hold for anything, right?
Yeah.
So you don't even need to check these things. And for, I think this is true even for empty models, huh? Because you need to check only for those models and assignments for which this holds, okay? And since if this does not hold,
Okay. Yeah. Yeah. That makes
Yeah.
sense.
False implies false is true.
it's something like that, okay? So then you don't have any requirement. Okay, so let's look at this. Ameya?
Sir, what does the arrow mean here? You mean implication, right? Or,
Logical implication, yes.
yeah.
Yeah,
Just a
it
second.
is true if P of X itself is false, but if PX is true, then it's the conclusion has to be true.
No, so this will be false, right? Because there could exist a y for which y is not in P of in P.
What? So Y will be, assume non-empty models to make it simple, okay? Because thinking for empty models requires a little bit more time. So let's suppose our models have at least domains which have at least one element, okay?
I mean, you could find some x for which px is false, and then this statement becomes true.
Correct, okay?
And
So,
if it is true for all x, if you can't find such an x, then it is all. Then it becomes. Then this for all y py also becomes.
I think you have the idea. Samir, did you understand that? See,
Yeah, I got it now.
P can be either empty or not empty. If P is,
Yes,
if it is if it is true for all elements, then this is true. Okay, an implication with true as a consequent is vacuously true. Okay, if not, P must be false for some, and can always make this thing to be true by picking that P, okay, that element X. And therefore, then you can make this vacuously true by making the thing. And that's why this thing is true. See, all these things, okay, here I'm giving you examples where, this is true for all validity, okay, pretty much validity or, logical consequence, okay, meaning. We'll see that SMT is, that is the job of predicate calculus, to prove valid statements regardless of for any interpretation. SMT theory is more constrained. We will get to that. We want to show these things for specific theories, and specific models that are of interest to us. That's what SMT solvers do. But I'm getting ahead. So let's finish this. So here I'm asking the question, maybe the first one I've already given. Okay, so which models satisfy the following sentences? That is for all. First of all, what does this mean? Okay.
For all x, for all y, x equal to y.
Actually, yes. This is true for an empty model also, right? For empty model, for all x is vacuously true. I think for non-empty models, this model is true only with exactly one element, because anytime it has more than one element, you can always pick two distinct elements from the domain to make this thing false, right?
Yes.
Yeah. So this model is not valid because it's not true for models in which the interpretation for the domain is, I mean, the domain is mapped to something whose cardinality is more. How about this?
Q is identity.
Excuse me?
Q is identity or like
You
true
can
for
be
all.
any. No, here only when you use equality that has this identity. There are two things that identity. If X and Y, interpretation of X and Y, I mean the value assignment of X and Y. So Q means it could be any arbitrary predicate. Yeah. Which means you can have different interpretations.
Could you repeat? I couldn't hear.
So only the models in which Q is associated, Q has all the elements, right?
Yeah. So which means what you're saying is
Q has all X and Y, like all combinations of X, Y.
No, not necessarily. What it says is the relation has to be. This is correct. You're right. You're right. Okay. For all, it has to. Yeah. You're right. Okay. So it has to include the whole thing. That's exactly right. Okay. So for all X, for all Y, QX. So it has to be true for all possible tuples, pairs, okay, of elements X and Y. That is the relation R that is associated, that is given as interpretation for Q, has to include the entire set of all pairs. Yeah, exactly right. That's how about this one? So there's this notion of what is called a relation is said to be total if it maps every element in the domain. A relation here, this is a relation is mapping some elements in the domain to something. Yeah. So here, what it's saying is, for every Q has to be such that for every X, it has to associate some Y. Okay. Which means that this is exactly the case when you say a relation is total. Okay, a relation is called total if it is doesn't leave anything in the domain for which it does not. So the domain of R has to be A. Should be the entire set. Okay, there must be at least one element for, that it makes that every every element in the domain to be associated. Yeah, this is exactly when the relation that is given as an interpretation for Q is total. Okay, that it does not leave any element in the domain undefined. Yeah.
Yep.
Okay. So this is yeah. What exactly SMT is doing is this problem. Okay, it is deciding or checking. These are procedures for checking this. This is exactly the formal version. So first for that, you keep showing theories. Okay, this has satisfiability, keyword, 3 keywords, satisfiability, modulo, and theories. What's a theory? And generally people say a theory is really a set of sentences. Okay, remember the sentences meant there are no free variables. Okay, they're all bound by some quantifier. Okay? Usually that's what a theory is, a set of formulas that where every variable in it is bound. Nothing is free. I mean, there could be for all X there exists a Y, etc., etc. Those things are possible. So for a given signature sigma, a sigma theory is a set of sentences, each of which is from a sigma formula. Okay, so given some language defined by a signature sigma, then a sigma theory is some subset of formulas, each of which is basically is constructed using that signature. And given that, then given a sigma theory, a T in a sigma formula phi, okay, that is both every formula in T as well as phi, they use the same syntax. T valid is denoted this way. The T, it's T valid. You can say T valid, or you can put a T here as a subscript to the double turnstile symbol. If for all models M of T and all variable assignments, phi holds for each of those things. That is, it is, see, earlier, validity was with respect to all models. Here we are restricting it to only those models for which for which every element in the theory T holds. Okay. So, in other words, the problem of satisfiability modulo theory is it's kind of parameterized with respect to a theory. Okay, so given some, something, or another way to say is, oh, I'm only interested in checking this validity for particular interpretations, for particular models. Okay, so maybe I want to restrict myself, my sigma to, and my models to the domain of natural numbers. Okay, but I want to check phi can be any formula, any arbitrary formula constructed using quantifiers, logical connectives, and so on. But I want to restrict myself to the interpretations which assign the number theoretic interpretation. Okay. So that's that's what this thing is. So these so the validity, satisfiability, and so it can all be extended with respect to those particular theories. If there exists some, so it is satisfiable if there exists some model, even a model of M of T. Some models that satisfy every element, every formula in T, such that sigma, such that phi, and some variable assignment for which phi of S holds in that model. So it is T unsatisfiable if, none of the models that make these every formula in here. So you could say that this checking is when you constrain yourself to looking at only those some set of models. Okay, and the way that models are defined is by give some meaning to specific meaning that you're interested in. Okay, so that's what these things mean. Do I have anything else? Yeah. So the validity problem. So here I define the notion of T validity, T valid, and so on. The validity problem of T is the problem of deciding, of checking, for each sigma formula phi, whether phi is T is T valid. Okay. Similarly, satisfiability and so on. And similarly, one can define quantifier-free validity problem and quantifier-free satisfiability problem if you restrict yourself to formulas in which there are no quantifiers. Okay, and phi is T valid if and only if not phi is T unsatisfiable. So to see an example, so for example here in the intro lecture, I gave you a lot of examples. So I say this one is an arithmetic theory. So see, when I ask this question, if this is satisfiable, if I, without giving anything, suppose I don't say, I give you just this formula. if I say if it's valid or in this case satisfiable, you will check if, okay, is there any interpretation for a model with some that gives some interpretation for equality. In this case, equality star, equality, and equality standard maybe star, such that, and for any assignment. But if I want this star to be interpreted as arithmetic multiplication operator over, even to be more specific, my domain is real, set of real numbers, and my star actually is given the interpretation corresponding to multiplication. Then is this satisfiable with respect to that? That is the question. So I'm restricting my interpretations to certain models. In this case, they are arithmetic. So this question of checking the satisfiability, validity of these things. In this case, these are every element here is, yeah, that is what satisfiability modulo theory is. Okay. Now, I mean, here I introduced it as a theory, as a set of formulas. Okay. Of course, you know, I kind of missed this point. Okay. We assume that this theory is closed under logical implication in the sense, if, I mean, you add into the theory everything that you can actually infer, okay, using so that it is, you know, just to make it convenient, okay, because automatically the models, everything that can be implied by a set of formulas, you know, all the models satisfy them as well. But what is the theory? Why is it that I'm saying as a theory? I mean, I could have you know, given this way. So you can have arithmetic can in theory be described, you can be axiomatized, okay, can be described as a set of axioms or axiom schemas, okay? So that is one way to say that. Or you can say, oh, I use my standard interpretation for real arithmetic. So given that interpretation, okay, or a more formal way of saying it is, oh, if I had an axiomatization that defines the set of models, okay, that my set of models are exactly those that satisfy those axioms, I mean those formulas in that theory, then what is the another, I mean, that is kind of a way of formal way of saying it. But another way is exactly this. I mean, if I give specific interpretations to these symbols restricted to certain models, then checking the satisfiability, validity, etc. Okay. So, for example, here, this is a mixed formula from a mixed theory. So there are arrays whose indices are drawn from maybe natural numbers. A range could be real numbers. Okay. So it's a combination of three theories, okay? The theory of arrays and the theory of natural numbers and the theory of reals, okay? So the select operation, etc., have specific meaning that you would attach to arrays. And for all the non-logical symbols you're talking about, okay, so although I have not used any arithmetic operations here, you could also use arithmetic operations. So then those will be given standard interpretation as you would give to natural numbers or and real numbers. Okay, so given that, then the satisfiability, when I ask the question if this is satisfiable, it means, oh, if you restricted yourself to those models and you know that follow the axioms and the things of natural number, reals, and so on, whether this is true or not. Okay, Now here, every sentence here is, because it doesn't use quantifiers, I would say it is quantifier free. But quantifier free really means that when you're asking this as, posing this as a satisfiability question, implicitly there is a quantifier. You could say that there is a quantifier, existential quantifier, outermost, because you're asking for the question if there is a model and a variable assignment that makes this thing to be true. Okay, and if you say if this is similarly, if you can have the validity problem, by saying that this is negation of this is unsatisfiable. If you make if this is unsatisfiable, then you implicitly, although you don't have any quantifiers here, you get the equivalent of checking that, that this is not true for any variable assignments for the given model, okay, that you're interested in. Okay, so that that's what we mean when you say quantifier free fragment. Okay, so there are no nested quantifiers here, but in a way that there is only one kind of a quantifier at the outermost. So that's what this thing, as opposed to these kinds of formulas which involve quantifiers. There are SMT solvers are also able to handle quantifiers in limited ways, but mostly that we will be interested in these kinds of things. Okay, so yeah, I'm going to stop there except for taking questions. Yeah.
Sir, so theory would be like, an example of a theory would be like, you have identities in it, like for all x, y, x plus y equal to y plus x, and
That's right.
some identities like that.
Correct, exactly. No, it doesn't have to be limited to just those identities. You can have more, you can have anything. For all x, there exists a y, there exists a z. I mean, you can make your theory whatever that you want, okay?
What if the theory is not valid?
Yeah, if a theory is not valid, I mean, the way the validity is defined.
No, I mean like not valid in the sense that there is some contradiction in that theory.
Yeah, that means that is exactly right. If you give a set of a theory, which if there's a contradiction, what does that mean? That means there is no, there is no model. Okay, that is what you're saying is if that set of if the theory is inconsistent, that means that there is no model that can satisfy all of them simultaneously. Okay, in that case, your problem is very simple. Okay, then your problem is one of checking if phi is true for the empty model. That's all.
Okay. Yes. So like we can also do union.
That would be not very interesting. Okay.
Yes.
I mean, the interesting theories are those which have a language and operations, and the meaning of those operations you can either give in a model theoretic way, okay, not give a theory, okay, or to make it formal, you're saying, oh, let me, to make it formal, you can say, oh, my, I'm interested in those models for which these axioms hold good, okay? These set of axioms hold good. That is a way of saying. Now, if I give you, say, natural numbers, I can make you understand what natural numbers are without actually giving you the theory that describes the natural number, okay? That's because there might be so many different axiomatization where you can give different theories, okay, of natural numbers. So, but maybe for specific, limited theories, you may like the one that you gave is a very good example, okay? Suppose I want a theory in which I have some function symbols, equality, and so on, but I don't have any interpretation, okay? But I only have the rules are only that my equality is reflexive, commutative, and associative, transitive, okay?
Okay.
Now that can be a theory which has only 3 axioms that you mentioned. There can be so many different models, okay? Where my domain could be something limited, only has 4 elements, it could be natural numbers, okay, under equality, real numbers under equality, they all satisfy that thing.
Okay.
And further, I can even say, oh, if I have multiplication, I could say, oh, my multiplication will have to be associative, okay?
Okay.
Only associative. It does not have to be reflexive or symmetric, okay?
Okay.
Now, that certainly natural numbers satisfy that, but there can be other models that don't satisfy either, okay? So that is what, okay, it means to give the theory, okay? That there are two ways of doing it, okay? You can either formalize it by giving actual axioms and then say, oh, I'm only interested in those models that satisfy those axioms, like you gave a perfect example, okay, which is this commutativity and so on. That is one way to make it formal, okay? And that is way by giving formulas. Or I can say if they're so standard, like natural numbers, arithmetic and so on, then you can give it. Now for arrays, it's a little bit. You see, arrays, depending upon how different programming languages may subtly interpret arrays differently. So there you will have to be careful. Yeah.
Yeah.
Yeah. Or the purpose of giving axioms and then saying it is if I want to deliberately leave certain ambiguity in my interpretation. Yeah.
Yeah. Okay.
Then it may be useful. I'll show you as we go along some examples where it is useful to leave certain things on it, because that way, if you check something, that will be true for more models. Okay, maybe you will prove something that is true for natural numbers, real, rational. Okay, but something may not be. I mean, true only for natural numbers, but not integers. Okay, right?
Yeah.
So that's what this thing is. So sometimes when we do give standard interpretation, we don't bother to give theories at all. Okay, because everyone knows what the meaning is. It's only when you have certain non-standard languages, then you will have to be careful, okay, in defining what the things is.
Yeah. This is like way too powerful.
Huh?
This idea is like this SMT solver is way too powerful.
Yeah, way too powerful. But remember that you're right. But it usually works for certain standard models. Okay, I mean, in theory, it can work for any thing. Okay, but if you make your theories, it is very easy to make theories easily undecidable. Okay.
Okay.
So as long as you will see that as long as your theories are decidable, in the sense there are procedures to check, okay, certain set of formulas, okay, then SMT solvers are built to check arbitrary formulas, arbitrary predicate logic formulas, assuming that for each of the theory there is decidable. Okay.
Okay.
That's how it is done. Otherwise, this becomes very uninteresting, as well as it is not solvable in practice. Okay. Therefore, while the theory, the way I have presented it, makes it seem the problem to be all powerful, okay, but in practice, you have to. It is solvable and useful only for limited things. Okay, and as you will see, it is mostly for quantifier-free fragments. The moment you go into quantifiers, it's a whole different ballgame. Okay, so but recently, people, there are solvers that have extended even Z3 for two alternation. Okay, two-level alternation. SMT solvers are fairly good. Okay, getting good, but for arbitrary nested quantifiers, it quickly becomes, the complexity is very high. Okay.
Okay.
And yeah. Okay, so that's good. So I think, Diganta, I know you probably had a demo ready.
Yeah. I sorry I couldn't reply to this, but
Yeah, that's fine. So we will have a demo. I think next class you do a demo. Yeah.
okay, sure. Yeah.
And we will announce that. So maybe hopefully there'll be more people joining. Yeah.
Yeah.
Okay. If there are no questions, I'm going to end the class.
Okay, sir. Thank you.
Thank you.
Thank you, sir.
Bye, sir.
Yeah. Okay. Bye bye.